have for tracking will work in real life. And then we calculate what is the crossing, and then we compute this disentanglement with y sub I tilde will be this expanding, and see how well this performs using real data. And turns out that I think for simple cases such as the one that I show, it can just basically disentangle because they keep their motions. So I would just expand this guy, create another token. So that looks like a simple scenario, and this works in that case. But when you start to have more complicated scenarios, like this one, so you have two people moving there, then you have one guy here. So this involves some other there. So this involves more people, 5 people. So we still want to see how well this thing will perform. We applied the basic algorithm that I just described. Probably this will not work, but the point here is that we can introduce some heuristics that will narrow down the set of hypotheses and that will still be able to disentangle that. One of the heuristics that we put is an agent never goes back and forth. So we see that these guys go continuously in motion. So an agent will cross this one and he will never go back. So we always want to check the string and make sure that we don't assign like something like j-1 to j to one agent. In this case, we're able to perfectly reconstruct the path of these 5 agents if we introduce these simple heuristics. So I think like the punchline here is that instead of doing all this complicated modeling that involves equations of motions that you probably will not need for this scenario, and having complicated sensors like cameras, you can still put the directional sensors, came up with heuristics such as the one I described before, and they never go back and forth, or maybe no more than 10 agents are going to be found, or the track only has length 10. And then maybe you can incorporate, well, if I have time information, you must take at least, let's say, 4 seconds to go from beam to beam. So basically we give this baseline algorithm, and then you can incorporate heuristics to try to give the best hypothesis of the behavior of agents. And we tested this with this example and some other examples, and seems to be giving pretty good results, despite the fact that we're not doing any modeling about the motion of the agent. Of course, there's more applications such as counting, and right now we're deploying a wireless architecture that has 2 passive infrared, a little microcontroller, and a chip communication device to do some wireless deployment of this. So beyond tracking that may be like a hard problem, can be solved if you put the right heuristics. But you can do counting, and then you can do some inference like cyber detectives or things like that under the framework in this hardware infrastructure, hardware architecture. And I think that's it. Well, I have some conclusions, but this is the research question: can we solve robotic tasks, avoiding excessive modular sensing? And we hope that the answer is yes. So here's our idea. Start with these Y values, and then we use these physical, virtual, and directional gates to guide the bodies and do some inference about their behavior. And then there's a lot of challenges for future work about where more system of bodies engage, which can analyze the simple bouncing primitives, and maybe I feel like LTL is interesting, but we can do more things because we have time there. So we've been exploring more complex logics to take into account real time. Because we can open gates in intervals of time, and that's not covered by LTL. So there's more challenge like what tasks can be solved when I start to involve things like time or other kind of sensors. And these are the concrete contributions, and one of the things that I would like to, where there is this contribution about these physical gates. We have another big part is the virtual gates and mobile robots. And then we have directional beams to do inference and tracking and counting. And I would like to, for future short term, look for applications, and we've been doing some work using landmarks, virtual gates, modifying the ball to have some communication capability. Maybe coverage can be like a good problem for this kind of bodies. We think it's just an interesting problem for these simple robots. Maybe controlling insects, we've been doing that, and maybe in the nano-robotics world, maybe those ideas may find some physical application, some physical instance. And also there's a lot of applications we think for filtering and guidance, and once we have these communication chips here, it's going to be interesting where to place these beams to do like maybe assisted living or control heating, cooling, and ventilations. But now we're going to have to understand how to place these beams, because there's going to be communications constraints, and what information should be sent back and forth to gather all these crossings. So it's going to be it's going to be interesting networking issues. Well, I think these are quick publications, and I think that's it. Okay, thank you very much for your time. How much time did I spend?
You spent 50, wait, hold on.
54.5 minutes.
Yeah.
54 and a half. Yeah, I think that